All right, and welcome to your bonus multiple choice review video. I know a lot of you have some difficulties with the multiple choice questions on the test, and just know that the actual multiple choice questions on the AP Stats exam are no more easier than those on the test. So this is just to get you in the mindset of more multiple choice. So these are out of the book. These are at the end of the chapter. So these aren't just somewhere new you don't know anywhere about. These are in the back of the book during the practice review. So we're going to look at 10 questions together. First question says, Dr. Stats plans to toss a fair coin 10,000 times in the hope that it will lead him to a deeper understanding of the laws of probability. Which of the following statements is true? A, it is unlikely that Dr. Stats will get more than 5,000 heads. Well, if he flips the coin 10,000 times, we would expect him to get 50-50, but is it unlikely that he'll get more than 5,000 heads? Well, what if he gets 5,001 heads? Would we consider that unlikely? No. It just meant, variation happens and maybe we get a little bit more heads than we used to. Now, if it had said, is it unlikely that he'll get more than 9,000 heads? Probably so. So definitely not A. B, whenever Dr. Stats gets a string of 15 tails in a row, it becomes more likely that the next toss will be head. Well, if each toss of the coin is independent, then it truly doesn't matter if there have been 15 tails in a row. It doesn't mean that you're due for a head. So that's the law of averages kind of kicking in there. So that is one of the myths, if you will, of the law of averages, that you're due for something. C, the fraction of tosses resulting in heads should be close to 1/2. Well, if we have a fair coin, which we do, they told us we had a fair coin up here, then yes, we would expect to see heads about half of the time. And notice they didn't say exactly 1/2, they said close to 1/2. So I'm liking this one so far. But let's see if we can eliminate the other two. The chance that the 100th toss will be a head depends somewhat on the results of the first 99 tosses. Again, that's the myth of the law of averages. You're not due for anything depending on the first whatever tosses that we get. And E, all of the above statements are true. We obviously know that is false. So therefore, yes, the correct answer is C. Number 2, China has 1.2 billion people. Marketers want to know which international brands they have heard of. A large study showed that 62% of all Chinese adults have heard of Coca-Cola. You want to simulate choosing a Chinese, which sounds weird, like a Chinese person, or we're just now calling them Chinese, a Chinese. Is it just me, or does that sound a little weird? Anyway, you want to simulate choosing a Chinese person at random and asking if he or she has heard of Coca-Cola. One correct way to assign random digits to simulate the answer, not the person, the answer is one digit simulates one person's answers. Odd means yes, even means no. Well, that means that we're at a 50-50, right? If there are as many odds as there are evens, but it's not 50-50. It's 62-38, really. So this is wrong. One digit simulates one person's answers. 0 to 6 means yes. Well, there are 7 numbers there, which means 70% if we're talking single digits. 7 to 9 mean no. Well, there's 30%, which again is not matching our 62%. So no. One digit simulates the result. 0 to 9 tells how many in the sample said yes. That, kind of doesn't make sense, but 0 through 9, that's 100%, right? That's all of our single digit numbers. So no, again, that's stupid. D, 2 digits simulate one person's answer. 00 to 61 means yes, 62 to 99 means no. Now let me jump to E because they look very, very similar to each other. The only difference is these parts right here. Now, if we want 62% to be a yes, then people might accidentally gravitate to this one because there's a 62, but it starts at 00. So there are really 63 numbers in this set. 00 to 61, there's only 62 numbers. So that is our correct 62-38 ratio. So our correct answer would be D. Let's double check. Yes, that is correct. Number 3, choose an American household at random and record the number of vehicles they own. Here's the probability model if we ignore the few households that own more than 5 cars. So just 0 to 5 cars. No more than 5, we ignore them. A housing company builds houses with 2-car garages. What percent of households have more than the garage can hold? Number 1, we need to discuss what kind of events the number of cars represent. All of these events here, 0 through 5, must be disjoint events. We can't own 0 cars and own 1 car. We either own 0 or we own 1 or we own 2 or 3 or 4 or 5. So all of these probabilities are completely separate from each other. There's really no overlap if we could somehow draw a ridiculous Venn diagram. So, a company builds 2-car garages. What percent of households have more cars than the garage can hold? Well, more cars than 2 would be 3 or more. So we may simply add together the probability of 3 cars plus the probability of 4 cars plus the probability of 5 cars. So 0.13 plus 0.05 plus 0.02 all together makes 20%, which would be answer choice C. Correct. Number 4, computer voice recognition software is getting better. Some companies claim that their software correctly recognizes 98% of all words spoken by a trained user. To simulate recognizing a single word when the probability of being correct is 0.98, let 2 digits simulate one word. 0 to 97 mean correct, and I guess we mean 98, 99 is wrong. There's our 2%. The program recognizes words or not independently. To simulate the program's performance on 10 words, use these random digits. The number of words recognized correctly out of the 10 is, so if we start reading 2-digit numbers, our first 2 digits are 60. That means if it's between 00 and 97, that means correct. So we got a good number. Next 2 numbers, 97. Well, that's at our very end here, but we're still good. There's 07, we're still good. 00, we're still good. 24, still good. 17, still good. 86, still good. 82, still good. 98, wah, wah. Now, how many have we got to this point? 1, 2, 3, 4, 5, 6, 7, 8, 9. And the last 2 numbers to get 10 words altogether, 43 works. So the number of words recognized correctly out of the 10 would be 9. And we're good. All right, 5, 6, and 7 are all going to use this information here. Okay, so I will repeat that information for the next 2 slides. So 5 says, what is the probability that a student has a GPA under 2? Well, here's GPA, here's under 2. Well, we have 2 classes of individuals, people who've skipped many classes and people who have skipped few classes. And those 2 events are disjoint. You can't skip many and few at the same time. You're either one or the other. So we may just add together our individual probabilities, or really we can just add together our 2 events there. So we have 225 people out of, well, we have to count up. They didn't give us the total, unfortunately, out of all these people. So if we add 80 and 175 and 25 and 450 and 5 and 265, we get a nice round 1,000. So 225, I don't need to do approximate. What am I doing? 225 out of 1,000 is exactly 0.225, which would be, no, I added that wrong. Sorry. That's 255. I can't add. So it would be answer choice B. Correct. Number 6, what is the probability that a student has a GPA under 2.0 or has skipped many classes? So the 2 things, GPA under 2 and skipped many classes. There's GPA under 2, here are those people, and skipped many classes, here are those people. Well, looky there. We will have included these 80 people twice if we just take this total, which would be, let's see, there's 105, so 110 total there, and here was our 255 from the last problem. If I just add together 255 and 110, I've included these 80 people twice. So what we could do is we could take our 255 plus 110, subtract away our 80 people we've included twice, and how many leftover people is that? Let's see, there'd be 365 minus 8, it'd be 285. And we're still out of all our 1,000 individuals, which makes for 0.285 as the probability. Now, another way you could look at this, if you wanted to, would be just to completely ignore the 110 and the 255 here and just do this. You could say, well, I want these people. Well, I don't want to count those people again, so now just add 25 and 5 more. So if we took 175, 80, 25, and 5 without including the 80 twice and added all that together, we would end up with our 285. So there's a second way you could do it. So 285.285, there we go. Number 7, what is the probability that a student has a GPA under 2.0 given that he or she has skipped many classes? Now, here is an example of our conditional probability. So if I were to write this, I'd write GPA under 2.0 given, there's that vertical line, we have skipped, if I can spell many classes. Now, anytime you have a conditional probability and you have a table, that means you only want to focus on that part of your table. You know the person has skipped many classes. So we can say, you know what, screw you, all you few people, we're just going to black you out. We don't even want to consider you. Forget about you. So here's our data here. So now with GPA under 2, well, there's 80 people. Out of only these people, not the 1,000, we know we're only dealing with many skipped class people. And altogether there we had 110. So 80 out of 110, well, that's 8/11ths, which is, I'm going to say, if I'm looking at this, I know this has to be greater than 50%. And all of these but one is greater than 50%, so it's got to be E, and that is the right answer. Number 8. This one, interesting problem. For events A and B related to the same chance process, which of the following statements is true? And I know this is the type of problem that you don't want to see on a multiple choice test. If A and B are mutually exclusive, then they must be independent. If A and B are independent, then they must be mutually exclusive. If A and B are not mutually exclusive, then they must be independent. If A and B are not independent, then they must be mutually exclusive. If A and B are independent, then they cannot be mutually exclusive. Yeah, all of those really feel like they're about saying the same thing, but they're not. Okay? Now, first, let's go back and describe what are mutually exclusive and what are independent events. Mutually exclusive events, we said there was another word for that we used a lot, which was disjoint. And disjoint events meant that if one event happens, the other one does not happen. They are completely separate in a Venn diagram. They do not touch. There is no overlap. Okay? And independent events just mean that if one event happens, that it has no effect on the other happening, maybe the second time around. Okay? Flipping a coin, for example, are independent events. Just because you get 5 heads in a row doesn't mean that you're due for a tail coming up. You still have a 50-50 chance of getting ahead on the 6th toss. Now, a lot of people want to view mutually exclusive and independent as really two cohesive things, like they're really meaning the same thing, but they're not. Oh boy. All I'm going to do for this one, because I know this one's tricky, but I'm going to go straight to which one's the actual answer, because I can explain this clearly, but I have a tough time explaining necessarily why the first 4 wrong. Okay? So let me just jump down to E here. It says if A and B are independent, then they cannot be mutually exclusive. I'm going to show you why this statement is true using one of our probability formulas. We talked about using this formula. The probability of A and B is equal to the product of the individual probabilities if A and B are independent. Okay? If A and B are independent. So we are saying if they are independent. So we're saying, hey, it's cool. We can use this formula. then they cannot be mutually exclusive. Well, mutually exclusive meant in a Venn diagram, and I'll just draw a Venn diagram here real quick. If they are really mutually exclusive, then there is no overlap. And that overlap part right there is the probability of A and B. So if they are not mutually exclusive, then that middle part would be 0, correct? So if we go back to this, then we're saying, if A and B are independent, then that value of probability of A and B is really 0. And we can't just take the product of these two things and get 0 out of the probability for that. So that's my explanation for why the answer is E. The rest of these, they're pretty tricky, and I understand, and I'm sorry that I'm just not going to take another probably 20 minutes to explain why each one of these is wrong. Okay? But just know that if A and B are independent, they cannot be mutually exclusive. Okay? They cannot be disjoint. Because if A and B again are independent, then this probability part would end up being 0, which cannot be true. All right, back to more of the mathy ones. Number 9, choose an American adult at random. The probability that you choose a woman is 52%. The probability that the person you choose is never married is 25%. Probability the person we choose is never married is 25%. Probability that we choose a woman who is never married is 11%. The probability that the person you choose is either a woman or has never been married or both is therefore about, we got a lot of information here. We need a way to organize it. Well, I've got two different things going on here. I've got gender, I got women, which they didn't mention males, but I've got males. And I have married and not married. So I'm going to make a nice two-way table. So we'll have married and we'll have not married. Okay. Doot, doot, doot. And we'll have total over here. And we have women and men. Okay. And total. So, the probability that you choose a woman's 52%. Well, they didn't mention if they were married or not married, so that must be our total, right? 52% of women total. The probability that you choose a person who is never married is 25%. Well, they didn't mention if the person was a woman or not, so that would be in our total column for never married. The probability that you choose a woman who has never married, which they're kind of saying both of those things at the same time, woman and never married, is 11%. Well, here's women, here's never married. Well, it must be talking about right there. Okay, the probability that the person you choose is either a woman or has never married. So we want the probability of woman or never married. Well, that means we need to find the probability of a woman plus probability of never marrying minus any intersection those two things may have. Well, I need to figure out some other numbers in here. So here's where we're going to use our mathematical skills. If 11% of women have never been married and 52% are women altogether, if we subtract those two things, we're left with 41% of women who have married to get our total 52%. Likewise, we can come over here to the never married. 25% of never married and 11% of which are women. That means 14% of the leftover 25% must be men. Okay, now we're to go with this. Men. If there's 52% women, that means we must have the leftover 48% are men. Here's our 1.0. If 52% have never married, that means 75% must have married regardless of gender. And then we can go this way or this way for our last group here, but we should get the same number. 75% minus 41% makes 34%. Does it check out this way? Yes, 34 and 14 makes 48. So now we have a full, complete table to use. So now the probability of a woman, well, that was 52% altogether, plus the probability of never marrying, that was 52%, minus the probability of being a woman and not marrying. Well, that is our 11%. So we really want to take our 52% plus our 25%, and subtract away our 11%, which puts us at 66%. Now, you might have originally looked at that and went, we didn't really need to create this table. We had women, we had never married. They gave us the probability of both woman and never married. I mean, they gave us all three of those probabilities to begin with. That's true. But I'm just going to throw a little spin out there. What if they had asked the probability that the person we choose is a man and has been married? Well, then our table would really come in handy. So if you recognize that you could have just added the first two probabilities and subtracted the third, good for you. If you didn't realize that, and this table makes sense to you and how we created it, good. Because there might be a chance on the multiple choice part of the test that, there would be a question like this, and there's maybe 3 questions related to it. And you would use the same information to help you solve the 3 questions about that particular problem. And the last problem. Deck of playing cards has 52 cards, of which 12 are face cards. We have 4 jacks, 4 queens, and 4 kings for a total of 12 face cards. If you shuffle the deck well and turn over the top 3 cards one after the other, what's the probability that all 3 are face cards? Well, so what probability? 3 face cards. So we can look at that as a probability that the first card is a face card. And that is, well, 12 out of 52. Okay. What's the probability that the second card is a face card? And if you said 12 out of 52 again, you would be mistaken. Because if we got the first card was a face card, then technically we need to write, and I kind of screwed myself on room here. Let me just bring that up, bring this over, and bring that back down. Then really I should have written this as probability that the second card is a face card given the first card is a face card. Well, if the first card's a face card, there's only 11 face cards left, and there are only 51 cards left. Because I didn't shuffle the first card back in the deck and redrew a second card, this says one after the other. And so what's the probability that the third card's a face card given the first and the second card are both face cards? Well, there's 10 face cards left over at that point with 50 cards left in the deck. So now multiplying our results together, we get something that's like 0.0099 yada yada yada, which closely resembles answer choice C. So I hope these 10 multiple choice questions that were from the book at the end of the chapter better help prepare you for what to expect on the multiple choice of the test. And that is all for the chapter. We are completely done. Adios and goodbye.